Hi everyone, welcome to the next presentation. Thanks for tuning in. I'm delighted to introduce Scott Genin from OTI Lumionics. He is the head of materials discovery, so very well suited for this event. And today he will tell us about designing how they design display materials without a wet lab. Scott, with that, the stage is yours.
Thank you, Christoph, for that introduction. I'm here to talk about kind of our efforts in terms of designing materials for actual mass production and for final OLED products. So one of the important things is that to understand is that advanced materials can really drive tech value through it and kind of derive value through the entire value chain. An advanced material can enable so many different technological changes within the products, with how we interact with our smartphone, with how we interact with our LCD screens. You know, a technological change such as the development of phosphorescent materials has enabled OLEDs to actually be commercially feasible. The conundrum is that these materials have very high development costs and they have very long development time costs. And two of the reasons is that when you actually enter mass production, or you're trying to get into a final product, it takes a long time to actually qualify a material for an end user or customer. And in the semiconductor industry, this is this can become very expensive, where a panel maker would have to spend a lot of time and a lot of money actually validating a material, and usually they'll only have a couple times per year to actually validate that. So one of the things that we've aimed for kind of the simulation of, as many materials discovery companies have, kind of using AI and simulations to design new materials. But one of the conundrums that we face within the OLED industry is that real data from experiments can be very expensive. It can not only be very expensive to actually synthesize the material, then validate its emission spectra. At the end of the day, the material actually has to go into a device, which requires new equipment, more expensive equipment to actually design an OLED stack, a proper OLED stack. And that just constantly increases the cost of verification. And so one of the things that often happens within the kind of materials discovery community is that we generate a lot of our data synthetically. So if you look at some of the most popular data sets that academics use to train machine learning models, they often will use density functional theory data. And this is an interesting, it's an interesting thought, but the conundrum is that one of the things that often unless you have a deep knowledge about these density functional theory models, is that your machine learning model will basically inherit all of the bad habits that density functional theory has. And this can be actually very problematic. So one of the things that we've really emphasized is that, high accuracy simulations are really the key in enabling us to have very well curated and manicured data sets so that we can actually train our machine learning models on. And so this is one of the things that we've been pursuing, is about how to use basically quantum computers or quantum inspired algorithms to generate very accurate data for OLED materials. One of the the reason why we're interested in using quantum computers is that the electronic structure problem is inherently a quantum mechanical problem. And there are tools today computational frameworks, such as variational quantum eigensolver, that can even run technically today, which enable us to actually solve this problem. The problem that we face is that a lot of quantum chemistry simulations that have been demonstrated on actual quantum hardware are very small, and they take much longer to solve on a quantum computer than what you can do by hand. And if you were to go onto something like Azure or AWS and try to estimate the cost to run something like the lithium hydride problem using the variational quantum eigensolver, it can cost up to $70,000. And this is something which no company would actually tolerate in reality, especially on a mass scale. If you can imagine having to simulate 1,000 materials today, this can get very expensive very quickly. But quantum chemistry, what a lot of people are predicting is that quantum chemistry will still be the killer app for materials, chemicals, and drugs. So the question is, how do we necessarily get there or